Let's start with something simple. Right now, wherever you are, there's energy flowing around you. There's warmth in the air, or maybe you're under a blanket and your own body is radiating heat into the fabric. There's light, probably from a screen or a lamp. Photons bouncing off every surface in the room. If you're plugged in somewhere, electricity is coursing through copper wires in the walls. 60 times a second the current is switching direction, back and forth, back and forth. And you don't even think about it. It's just there. It's always been there, for your entire life. You flip a switch, the lights come on. You turn a dial, the stove heats up. You press a button, and a machine that fits in your pocket connects you to someone on the other side of the planet. But here's the thing. For almost all of human history, none of that existed. And the story of how we got from firelight to fusion reactors, from burning sticks to powering cities, that story is one of the most extraordinary things our species has ever done. It's messy, it's full of accidents and arguments, it spans thousands of years, and honestly, it's the kind of story that's perfect for right now. So settle in, get comfortable. We're going to walk through the entire history of energy engineering, slowly, from the very beginning. And if you drift off somewhere along the way, that's perfectly fine. The story will still be here. So where do we start? We start with fire. And I know that sounds obvious, almost too obvious, but fire really is the first energy technology. It's the moment when a living creature figured out how to take energy stored in one form, the chemical bonds inside wood, inside dried grass, inside animal fat, and release it as heat and light on demand. That's engineering. It's crude, sure, but it's engineering. You're identifying an energy source, you're figuring out how to convert it, and you're using the output for something useful. Now, we don't know exactly when humans first controlled fire. The evidence is genuinely tricky to pin down because how do you tell the difference between a natural brush fire and one that somebody started on purpose 1,000,000 years ago? But there are some remarkable archaeological sites that give us clues. Wonderwork Cave in South Africa has evidence of fire use going back roughly 1,000,000 years. Ash layers, burned bone fragments, charred plant material, deep inside a cave where a natural wildfire wouldn't reach. That's early Homo erectus territory. 1,000,000 years. Think about that for a second. Our relationship with energy conversion is older than our species. Homo sapiens have been around for maybe 300,000 years. Fire came first. And what fire gave us was extraordinary. It gave us warmth, obviously, which meant we could survive in colder climates, stay active after dark, sleep more safely, because predators tend to avoid flames. But it also gave us cooking. And cooking. This is one of those details that sounds minor, but actually changes everything. Cooking breaks down the tough cellular structures in food, especially in meat and starchy roots. It effectively pre-digests your meal. That means your body spends less energy processing food and extracts more calories from what you eat. Some anthropologists, like Richard Wrangham at Harvard, have argued that cooking is one of the key reasons our brains were able to grow so large. Brains are metabolically expensive. Yours right now is using about 20% of your resting energy, even though it's maybe 2% of your body weight. You need a lot of high-quality calories to run a big brain, and cooking made that possible. So fire isn't just the first energy technology. It might be the energy technology that made us who we are. But for a very, very long time, fire was basically the only energy technology. For hundreds of thousands of years, the engineering challenge was simple. Find fuel, keep the fire going, don't let it go out. and the fuel was almost always biomass, wood, dry dung, animal fat, plant material. The energy density wasn't great, but it was everywhere, and it was renewable in the most basic sense. Trees grow back, grass grows back. As long as you didn't strip the land bare, you could keep burning. The next big leap, and this one took a genuinely long time to arrive, was figuring out how to harness energy from something other than combustion. And that something was moving water and moving air, wind and water power. Now, you might think of windmills and water wheels as quaint, old-fashioned things, the kind of stuff you see in paintings of the Dutch countryside or old English villages. But these machines were revolutionary. They represented a completely different way of thinking about energy. Instead of burning something, you're capturing kinetic energy, the energy of motion, from the natural environment and converting it into useful work. That's a conceptual leap that's hard to overstate. The earliest water-powered devices we know about show up in the historical record around the 3rd and 2nd centuries BCE. The Greeks and Romans both developed water mills for grinding grain. There's a description by the Greek poet Antipater of Thessalonica, writing around the 1st century BCE, and he's basically celebrating the water wheel as a labor-saving miracle. He writes about how the mill girls can sleep in now because the water nymphs are doing the grinding, which is a lovely image, right? The first time in history that a machine is doing work that human muscles used to do, and a poet notices and writes about what it means for the people who used to do that work, that tension between the machine and the laborer, between efficiency and employment. That's a thread that runs through the entire history of energy engineering, all the way to today. The basic mechanism of an early water wheel is beautifully simple. You've got a stream or a river, and the water is flowing. You place a wheel with paddles or buckets at the edge of that flow, and the moving water pushes against the paddles and turns the wheel. The wheel's axle is connected to a millstone, and as the axle turns, the millstone rotates against a stationary stone, and grain between them gets crushed into flour. That's it. You're converting the kinetic energy of flowing water into rotational mechanical energy, and then using that rotation to do useful work. But even within that simple concept, there's real engineering subtlety. The earliest wheels were what we call undershot wheels. The water flows beneath the wheel and pushes the bottom paddles. These work, but they're not very efficient. You're only capturing a fraction of the water's energy. Later, engineers figured out that if you channel the water to the top of the wheel and let it fill buckets that then fall under gravity, you get a much more powerful arrangement. These are overshot wheels, and they can capture maybe 60 to 70% of the available energy. That's a huge improvement. And the difference comes down to physics. With an overshot wheel, you're not just using the kinetic energy of the flowing water. You're also using the potential energy, the weight of the water, as gravity pulls it down. You're getting two energy sources for the price of one. The Romans, being the Romans, scaled this up dramatically. There's an extraordinary archaeological site at Barbegal in southern France, dating to the 2nd century CE, where the Romans built a complex of 16 overshot water wheels arranged in 2 parallel rows on a hillside. The water cascaded down from wheel to wheel, and the whole system could grind enough flour to feed the entire nearby city of Arelate, modern-day Arles, which had a population of maybe 30 or 40,000 people. That's an industrial-scale flour mill, powered entirely by falling water, built nearly 2,000 years ago. When archaeologists first surveyed the site, some of them called it the greatest known concentration of mechanical power in the ancient world. And here's what's really fascinating about Barbegal. It shows that the Romans had the engineering knowledge to build something like an industrial revolution. They had water wheels, they had gears, they had the metallurgy to build iron tools. They had roads and aqueducts and concrete. So why didn't they? Why didn't the Roman Empire industrialize the way Britain did 1800 years later? That's one of those big, tantalizing questions that historians love to argue about. Part of the answer is probably slavery. When you have abundant, cheap human labor, the economic incentive to build labor-saving machines is much weaker. Part of it might be about the availability of certain fuels, particularly coal, which the Romans knew about but never used at scale. And part of it might just be about the particular combination of pressures and incentives that have to line up for a technological revolution to happen. It's not enough to have the knowledge. You need the motivation, the materials, the economic conditions, and sometimes just the right person in the right place at the right time. But anyway, the point is that water power was real, it was significant, and it kept developing. After the fall of the Western Roman Empire, the technology didn't disappear. It spread. The Domesday Book, that extraordinary survey of England compiled in 1086 for William the Conqueror, records nearly 6,000 watermills across England. 6,000. For a population of maybe 1.5 to 2 million people. That's roughly 1 mill for every 300 people. Water power wasn't a curiosity, it was infrastructure. It was the backbone of the medieval economy. And alongside water came wind. Windmills show up a bit later in the historical record. The earliest known windmills were built in Persia, modern-day Iran and Afghanistan, probably around the 7th century CE, maybe earlier. These were vertical axis mills, meaning the sails spun around a vertical shaft, like a revolving door. They were used for grinding grain and pumping water, and they were cleverly designed to work with the strong, consistent winds that blow across the Iranian plateau. The sails were shielded on one side by a wall, so the wind could only push them in one direction. Simple, effective, elegant. The horizontal axis windmill, the kind you probably picture, with the big sails turning like a pinwheel, that seems to have developed independently in northwestern Europe, probably in the 12th century. England, France, the Low Countries. And these became enormously important, especially in the Netherlands, where windmills weren't just grinding grain, they were pumping water. The Dutch used windmills to drain lakes and marshes, literally creating new land, the polders, by pumping water up and over dikes and into canals. At their peak, there were something like 10,000 windmills operating across the Netherlands. The entire geography of the country, the fact that so much of it exists below sea level and is habitable at all, is a testament to wind-powered engineering. Now, I want you to notice something about everything we've talked about so far: fire, water, wind. These are all ways of capturing energy that's already flowing through the natural world. The sun heats the earth unevenly, which creates wind. The sun evaporates water, which falls as rain, which flows downhill in rivers. Plants capture sunlight through photosynthesis and store it as chemical energy in their tissues, which we release by burning. Every energy source we've discussed is, ultimately, solar energy in disguise. The sun is doing all the heavy lifting. Humans are just figuring out cleverer and cleverer ways to intercept that energy and redirect it. And for thousands of years, that was enough. Biomass, wind, water. These powered civilizations, built empires, fed millions of people. But they had limits. Wood runs out if you cut it faster than it grows, and by the 16th and 17th centuries, parts of Europe were running into exactly that problem. England in particular was experiencing something close to an energy crisis. The forests were shrinking. The price of firewood was climbing. London was growing fast, and it needed fuel for heating, for cooking, for the workshops and small industries that were multiplying across the city. And this is where something buried underground, something black and dirty and ancient, begins to change everything. Because beneath the hills of northern England, beneath Wales, beneath Scotland, there were seams of a strange rock that burned. People had known about it for centuries. The Romans had used it in Britain, and there are references to sea coal washing up on beaches in northeast England as early as the 12th century. But for most of history, coal was a second-choice fuel. It smelled terrible. It filled your house with acrid smoke. If you could burn wood, you burned wood. But when wood got expensive enough, and when the population of cities like London got large enough, coal started to look a lot more attractive. By the late 1500s, coal was being shipped down the coast from Newcastle to London in enormous quantities. The phrase, carrying coals to Newcastle, became a proverb for doing something pointless, because Newcastle already had more coal than it knew what to do with. And as demand grew, miners dug deeper. And as they dug deeper, they hit a problem that would, in the most unexpected way, launch the modern world. The mines kept flooding. Water seeped in from underground aquifers, and the deeper you went, the worse it got. You could use horses to pump the water out, or you could use bucket chains powered by water wheels if you had a stream nearby. But these methods had limits. What the mining industry desperately needed was a powerful, reliable pump that could work anywhere, regardless of whether there was a river or a hilltop wind. And that need, that specific, practical, economic need to get water out of coal mines, is what gave birth to the steam engine, which is, without exaggeration, one of the most important inventions in the history of civilization. But the story of how it came to be is stranger and more human than you might expect, because it doesn't start with one genius having a flash of insight. It starts with a series of people, spread across decades, each one building on what came before, each one solving part of the puzzle and leaving the rest for someone else. The first name in that chain is a man you've probably never heard of, and his story begins in a small town in Devon, in the southwest of England. His name was Thomas Savery, and he was a military engineer, not a philosopher, not a university man, but someone who worked with his hands and understood practical machinery. Savery had been thinking about the power of steam for a while, probably inspired by earlier demonstrations and writings about what happened when you boiled water in a sealed vessel. And in 1698, he patented a device he called the miner's friend. It was, essentially, the world's first commercially intended steam-powered pump. Now, here's how it worked, and it's worth understanding the mechanism because it's beautifully simple, even if it had serious flaws. Savery's device had no moving parts in the modern sense. No piston, no crankshaft, nothing like that. Instead, it used two principles. First, you'd fill a sealed vessel with steam from a boiler. Then you'd cool the vessel by pouring cold water over it. As the steam inside condensed back into liquid water, it shrank dramatically. Steam takes up roughly 1,700 times more volume than the same mass of liquid water, so when it condenses, it creates a powerful partial vacuum. That vacuum would suck water up from the mine below, through a pipe. Then, in a second phase, you'd force more steam into the vessel at pressure, pushing the water that had been sucked up out through a second pipe to the surface. Fill, condense, suck, pressurize, push. That was the cycle. And it worked. Sort of. Savory demonstrated it for the Royal Society, and King William III reportedly saw a demonstration too. But there were real problems. The biggest one was that to pump water from any serious depth, and the mines that needed pumping were getting deep, sometimes 60 or 70 meters, you needed very high steam pressure. And in 1698, the metallurgy just wasn't there. The boilers and vessels of the time were made of hammered copper and riveted iron, and they couldn't reliably handle high pressures. They leaked. They burst. They were genuinely dangerous. Savory's engine could realistically only lift water from shallow depths, maybe 10 meters or so, before you were gambling with an explosion. For a deep coal mine, that wasn't nearly enough. So the miner's friend was more of a proof of concept than a practical solution. Savory knew it worked in principle, but the materials of his era betrayed him. And this is where the story gets more interesting, because the next person in the chain had a completely different approach. His name was Thomas Newcomen, and he was a blacksmith and ironmonger from Dartmouth, also in Devon, just a few miles from where Savory had worked. Newcomen wasn't famous. He didn't have wealthy patrons or connections to the Royal Society. He was a tradesman who sold tools and hardware to the mining industry, which meant he understood the flooding problem intimately. He talked to miners. He saw the limitations of horse-powered pumps firsthand. And sometime around 1700, maybe a little earlier, he started tinkering with an idea that would turn out to be transformative. What Newcomen built was fundamentally different from Savory's device because it used a piston inside a cylinder. Think of it this way. Imagine a large vertical cylinder, open at the top, with a piston inside that can slide up and down like a plunger in a syringe. The piston is connected by a chain to one end of a massive rocking beam, a big wooden lever, pivoted in the middle like a seesaw. The other end of the beam is connected to a pump rod that goes down into the mine. When one end of the beam goes down, the other goes up, and vice versa. So if you can make the piston move up and down inside the cylinder, you can rock the beam, and the beam works the pump. That's the basic layout. Here's the clever part. Steam from a boiler is let into the cylinder beneath the piston, filling the space. The steam doesn't need to be high pressure, just enough to fill the cylinder and push the piston up gently, helped by the weight of the pump rod pulling down on the other side of the beam. Then, and this is the key moment, a jet of cold water is sprayed directly into the cylinder. The steam condenses almost instantly. That enormous volume reduction, that same 1,700 to 1 collapse, creates a sudden vacuum beneath the piston. And now atmospheric pressure, just the weight of the air above the piston, pushing down on it, drives the piston down with considerable force. That downward stroke rocks the beam, which lifts the pump rod, which pulls water up from the mine. Then steam fills the cylinder again, the piston rises, and the cycle repeats. You see what Newcomen did? He didn't need high-pressure steam. He only needed enough steam to fill the cylinder at roughly atmospheric pressure. The actual work was done by the atmosphere pushing the piston down into the vacuum. That's why it was called an atmospheric engine. And that distinction mattered enormously, because it meant the boiler didn't need to withstand dangerous pressures. It was safer. It was buildable with the materials and skills available in early 1700s England. It was practical. Newcomen's first successful engine was installed in 1712 at a coal mine near Dudley Castle in the West Midlands. And it worked. It really worked. It pumped water from depths that Savory's device never could have managed, and it did it continuously, hour after hour, day after day. The engine made a slow, rhythmic rocking motion, maybe 12 strokes per minute, with that great beam seesawing back and forth, steam hissing, cold water spraying, the pump rod plunging into the earth and drawing up water with each cycle. Miners could go deeper. Mines that had been abandoned because of flooding could be reopened. The economic impact was immediate and significant. But here's the thing about Newcomen's engine that's easy to overlook. It was astonishingly inefficient, and I mean really spectacularly wasteful. Think about what's happening inside that cylinder. You fill it with steam, heating the metal walls, then you spray cold water in, cooling everything down, then you fill it with steam again, and all that heat energy has to re-warm the cylinder walls before the steam can even begin to fill the space properly. You're heating and cooling the same chunk of iron over and over and over, and most of the energy from the coal you're burning goes into reheating that cylinder, rather than doing useful work. Estimates vary, but Newcomen's engine converted maybe 1% of the energy in the coal into actual mechanical work. 1%. 99% was wasted, mostly into heating and reheating that cylinder and warming the condensation water. Now, you might think, that's terrible. Why would anyone use it? And the answer is beautifully pragmatic. It was sitting right next to a coal mine. Fuel was essentially free. You could shovel coal into the boiler all day long because there were literal mountains of coal right there. The inefficiency didn't matter when your fuel cost was close to zero. What mattered was that the pump worked, and it did. Newcomen engines spread across the mining regions of England and eventually to continental Europe. By the middle of the 1700s, there were hundreds of them chugging away, rocking their great beams, keeping the mines dry. But that inefficiency would eventually matter, a lot, because people started wanting to use steam engines for things other than pumping water out of coal mines. What if you wanted to power a factory that wasn't sitting on top of a coal deposit? What if you had to buy your coal and have it transported? Suddenly, an engine that wastes 99% of its fuel starts looking very expensive to run. And this is where the most famous name in steam engine history enters the story, not as an inventor who created something from nothing, but as an improver who saw exactly what was wrong and figured out how to fix it. James Watt. You've heard the name. There's a unit of power named after him. Every light bulb, every appliance, every power rating you've ever seen uses his name. But the real story of Watt is more nuanced and more human than the mythology suggests. He wasn't a wealthy gentleman scientist. He was a Scottish instrument maker, born in Greenock in 1736, and he made his living repairing and building precision instruments for the University of Glasgow. He was good with his hands, meticulous, and deeply curious about how things worked. The famous story, and it is well documented, not apocryphal, is that in 1763 or 1764, Watt was asked to repair a small model of a Newcomen engine that belonged to the university's natural philosophy department. The model didn't work well. It kept stalling, running out of steam, failing to complete its cycle. And as Watt studied it, trying to figure out why, he began to understand the fundamental thermodynamic problem. The cylinder was doing double duty. It had to be hot enough to keep the steam from condensing prematurely, and then cold enough to condense the steam and create the vacuum. Those two requirements were in direct conflict. Every cycle, you were fighting yourself. Watt later said that the solution came to him during a walk on Glasgow Green on a Sunday afternoon in 1765. Whether that exact moment happened precisely that way, who knows? Memory reshapes things. But the insight was real, and it was profound. What if you didn't condense the steam inside the working cylinder at all? What if instead, You connected the cylinder to a separate vessel, a separate condenser, that was kept permanently cold? When you wanted to create the vacuum, you'd open a valve and let the steam rush from the hot cylinder into the cold condenser, where it would collapse. The cylinder itself could stay hot all the time. The condenser could stay cold all the time. No more wasteful heating and cooling of the same piece of metal over and over. It sounds so simple when you say it like that. Just add a separate condenser. But that single idea, keeping the hot parts hot and the cold parts cold, roughly tripled the fuel efficiency of the steam engine. And more importantly, it opened the door to making steam engines economical in places where coal wasn't free. It meant steam power could leave the coal fields and go anywhere. Now, having the idea was one thing. Building a working engine was something else entirely. And this is where Watt's story gets difficult, because he spent years struggling to turn his concept into a reliable machine. The problem was precision. To make a piston seal properly inside a cylinder, the cylinder had to be bored to very tight tolerances, and the metalworking technology of the 1760s wasn't really up to the task. Watt was also perpetually short of money. He took on work as a surveyor and civil engineer to pay the bills. He entered into a partnership with John Roebuck, an industrialist who funded his experiments in exchange for a share of the patent. But Roebuck went bankrupt. The whole project nearly died. What saved it? What saved the entire trajectory of the Industrial Revolution, you could argue, was a partnership. In 1774, Watt connected with Matthew Boulton, a Birmingham manufacturer who ran a large metalworking factory called the Soho Manufactory. Boulton was everything Watt wasn't: charismatic, business-savvy, well-connected, and optimistic. He saw the commercial potential of Watt's engine immediately and had the resources to develop it properly. And crucially, Boulton knew another man, John Wilkinson, who had just developed a new boring machine capable of producing cylinders with unprecedented accuracy. Wilkinson's machine could bore a cylinder 50 inches in diameter to a tolerance that, as Boulton reportedly bragged, didn't deviate by the thickness of a worn shilling. That precision was what Watt had been missing for a decade. By 1776, the first commercial Boulton and Watt engines were being installed, and they were a revelation. Mine owners could see the difference immediately. Dramatically less coal consumption for the same pumping work. Boulton and Watt didn't sell their engines outright at first. Instead, they charged customers a royalty based on how much coal the new engine saved compared to a Newcomen engine doing the same job. Think about that business model for a second. They were literally charging people a fraction of the money they were saving. It was ingenious, and it made both men wealthy. But Watt wasn't done improving things. Over the next 2 decades, he and Boulton introduced a series of refinements that transformed the steam engine from a specialized pump into a versatile power source. One of the most important was the double-acting engine, where steam was admitted to both sides of the piston alternately, so you got a power stroke in both directions instead of just one. Another was the sun and planet gear, a mechanism for converting the reciprocating motion of the piston into rotary motion, turning a shaft, which meant the engine could now drive machinery directly, not just pump water. And then there was the centrifugal governor, that beautiful little device with 2 spinning balls on hinged arms that automatically regulated the engine's speed. If the engine ran too fast, the balls flew outward and partially closed the steam valve. If it slowed down, the balls dropped and opened the valve wider. It was one of the earliest examples of automatic feedback control, and the principle behind it shows up everywhere in modern engineering, from thermostats to cruise control. By the 1790s, Boulton and Watt engines were powering textile mills, flour mills, breweries, and ironworks across Britain. Steam had broken free from the mines. It was becoming the universal prime mover, the thing that could replace water wheels and windmills and horse teams and human muscle in almost any application. And this is where the story of energy engineering takes a turn that nobody in the 1700s fully anticipated, because once you have a reliable, portable source of mechanical power, a question starts forming that will reshape the entire world. What happens if you put that engine on wheels, or better yet, on a set of iron rails? That question had been simmering for a while, actually. Even before Watt perfected his engine, people had been experimenting with putting steam-powered vehicles on roads. A French military engineer named Nicolas Joseph Cugnot built what's often called the first self-propelled vehicle back in 1769, a massive, awkward, three-wheeled steam cart designed to haul cannons for the French army. It was slow, maybe 2 or 3 miles per hour, and it had to stop every 10 or 15 minutes to build up steam again. There's a famous story, possibly embellished, that Cugnot crashed it into a wall during a demonstration, which would make it not only the first automobile, but also the first automobile accident. Whether or not that particular detail is true, the machine was clearly impractical, and the project was shelved. But the idea didn't go away. And here's where the story gets really interesting, because the person who cracked the problem of mobile steam power wasn't James Watt. In fact, Watt actively opposed it. He thought high-pressure steam was dangerous. And to be fair, with the metallurgy of his day, he had a point. His engines worked at pressures barely above atmospheric, maybe 5 or 6 pounds per square inch above ambient. That was safe, that was manageable, and that was enough for a stationary engine connected to a mine or a mill. But if you wanted to put an engine on wheels, you had a weight problem. Watt's engines, with their separate condensers and their massive beam structures, were enormous. You couldn't just strap one to a cart. The breakthrough came from a realization that if you were willing to use steam at much higher pressures, say 40 or 50 pounds per square inch, you could build a much smaller, lighter engine that produced the same amount of power. You wouldn't even need a condenser. You could just exhaust the spent steam straight into the atmosphere. That meant fewer parts, less weight, and a machine compact enough to move. The man who made this work, more than anyone else, was a Cornishman named Richard Trevithick. And Trevithick is one of those figures in engineering history who deserves to be far more famous than he is. He was born in 1771, right in the heart of Cornwall's mining country, the son of a mine captain. He grew up around Newcomen and Watt engines, watching them pump water out of the deep tin and copper mines. He was physically enormous, 6'2", incredibly strong, and by all accounts, he was brilliant with machines, but hopeless with money. That combination would define his entire life. Trevithick understood something that Watt refused to accept, that high-pressure steam, properly contained, wasn't just safe enough. It was the future. By the late 1790s, he was building what he called puffers, high-pressure engines that exhausted directly to the air with that characteristic chuffing sound. And on Christmas Eve, 1801, he did something remarkable. He put one of his high-pressure engines on a road carriage and drove it up Camborne Hill in Cornwall, carrying several passengers. It was the first successful demonstration of a steam-powered road vehicle carrying people. The locals called it the Puffing Devil. Now, that particular vehicle had a short life. The story goes that Trevithick and his friends parked it under a shed, went to a pub to celebrate, forgot to extinguish the fire, and the whole thing burned up. Which is such a perfectly human detail, right? One of the most important machines in history, destroyed because its inventor wanted a drink. But the concept was proven. And then, Trevithick did something even more consequential. In February 1804, he built a steam locomotive that ran on iron rails at the Penydarren Iron Works in South Wales. It hauled 10 tons of iron and about 70 men along a tramway for roughly 10 miles. This was the first railway journey by a steam locomotive, and it worked. The engine performed beautifully. The problem was the track. The cast iron rails kept breaking under the locomotive's weight. That's a detail worth pausing on, because it tells you something important about how engineering progress actually happens. It's almost never just one technology that needs to advance. Trevithick had solved the engine problem, but the infrastructure couldn't keep up. The rails of 1804 were designed for horse-drawn carts, not multi-ton steam engines. It would take another decade of improvements in rail design and iron making before railways became truly practical. And here's the sad part of Trevithick's story. Despite being the first to build a working railway locomotive, he never profited from it. He moved on to other projects, eventually traveled to South America to install mining engines in Peru, lost everything, and had to be bailed out by a young Robert Stephenson, whom he happened to meet in Colombia. He died in 1833, essentially penniless, and was buried in an unmarked grave. Meanwhile, the technology he pioneered would generate some of the greatest fortunes of the 19th century, because the person who truly commercialized the steam railway was George Stephenson, a self-educated Northumberland engine wright who'd grown up so poor he didn't learn to read until he was 18. Stephenson didn't invent the steam locomotive. Trevithick did, and several others built working engines in the intervening years, including John Blenkinsop and William Hedley. But Stephenson was the one who made the whole system work reliably, economically, and at scale. He understood that the locomotive was only part of the problem. You also needed the right track gauge, the right rail profile, the right gradients, the right signaling. He thought about the railway as a complete system, not just an engine on wheels. His most famous moment came in 1829 at the Rainhill Trials, a competition organized by the directors of the Liverpool and Manchester Railway to determine what kind of motive power their new line should use. Some people still thought stationary engines pulling trains with cables were the way to go. Stephenson entered his locomotive, the Rocket, built with his son Robert, and it dominated the competition. The Rocket wasn't the fastest or most powerful locomotive ever built at that point, but it was the most reliable and the most well-engineered as a complete package. It incorporated a multi-tube boiler, an idea suggested by Henry Booth, the railway's treasurer, which dramatically increased the heating surface and thus the steam generating capacity. Instead of passing hot gases through one big flue, you pass them through 25 smaller copper tubes running through the water. More surface area, more heat transfer, more steam, more power for the same boiler size. It's the same principle behind why a car radiator has all those thin fins. You're maximizing the area where heat can move from one substance to another. The Liverpool and Manchester Railway opened in September 1830, and it changed everything. This was the first intercity railway to rely entirely on steam locomotives to carry both passengers and freight on a regular timetable, and to operate as a common carrier, meaning anyone could buy a ticket. It was an immediate commercial success, and it was also the site of the first railway fatality of a prominent person. William Huskisson, a member of Parliament, was struck by the rocket during the opening ceremony. He died that evening. Even in its moment of triumph, the railway demonstrated that this new kind of power demanded new kinds of caution. But the railways spread with astonishing speed. By 1850, Britain had over 6,000 miles of track. The United States, starting later but building faster, had over 9,000. And think about what this meant in energy terms. For the first time in human history, you could move heavy loads over land at speeds faster than a galloping horse, sustained for hours, powered by nothing more than burning coal and boiling water. Before railways, overland transport was so expensive that it was often cheaper to ship goods hundreds of miles by sea than to cart them 50 miles by road. Railways collapsed the cost of moving things by a factor of 10 or more. They made it economical to ship coal from mines to cities, iron from furnaces to factories, grain from farms to ports. They created national markets where before there had only been local ones. And here's what's really fascinating from an energy perspective. Railways didn't just consume energy more efficiently than horses. They fundamentally restructured how energy flowed through civilization. Coal that had been trapped in regional pockets could now reach anywhere the rails went. Factories no longer needed to sit next to rivers or coal seams. Cities could grow beyond what their immediate hinterland could feed. The railway was an energy distribution network as much as it was a transportation system. Now, while all this was happening on land, something equally important was happening on water. Steam-powered boats had actually preceded steam locomotives by a couple of decades. Robert Fulton's Clermont made its famous voyage up the Hudson River in 1807, and by the 1820s, steamboats were transforming river commerce in America, particularly on the Mississippi. But ocean-going steamships took longer to develop because the problem was fuel. A sailing ship carries its energy source for free, the wind. A steamship has to carry coal, and coal is heavy. For long voyages, you'd need so much coal that there wasn't enough room left for cargo. It seemed like a mathematical impossibility. And this is where one of the most remarkable engineers of the 19th century enters the picture, Isambard Kingdom Brunel, a man whose ambitions were so enormous they sometimes bordered on the absurd. Brunel understood a principle of scaling that most people missed. The carrying capacity of a ship increases with the cube of its dimensions because capacity is about volume. But the resistance a ship encounters moving through water increases roughly with the square of its dimensions because drag is mostly about the cross-sectional area pushing through the water. So if you build a ship twice as big in every dimension, you get 8 times the volume, but only about 4 times the drag. Which means a bigger ship is actually more fuel efficient per ton of cargo than a smaller one. The solution to the coal problem wasn't to use less coal. It was to build a much, much bigger ship. Brunel's Great Western, launched in 1837, was the largest steamship in the world and proved that transatlantic steam travel was commercially viable. It arrived in New York with 200 tons of coal still in its bunkers. Plenty of margin. His follow-up, the Great Britain of 1843, was even more revolutionary. The first large ocean-going ship built of iron rather than wood, and the first to use a screw propeller instead of paddle wheels. Every major design choice in modern shipbuilding traces back to that one vessel. And then Brunel, never one to think small, conceived the Great Eastern, a ship so massive, nearly 700 feet long, that nothing larger would be built for over 40 years. It was designed to carry enough coal to steam all the way to Australia without refueling. The Great Eastern was a commercial failure, plagued by construction problems and bad luck. but it found an unexpected second life, laying the first successful transatlantic telegraph cable in 1866, connecting the old world to the new with instantaneous communication. But we're getting ahead of ourselves a little, because while Trevithick and Stephenson and Brunel were figuring out how to move steam power across land and sea, something was happening in the world of scientific theory that would eventually make steam itself look primitive. Researchers were beginning to ask a deceptively simple question. What, exactly, is heat? And how much useful work can you actually extract from it? The answers would give birth to an entirely new branch of physics, one that governs everything from power plants to refrigerators to the ultimate fate of the universe. And the person who started that revolution was a quiet, melancholy young Frenchman who published one short book, was almost completely ignored in his lifetime, and died of cholera at the age of 36. His name was Sadi Carnot, and the story of how he figured out the absolute limits of what any engine can do is one of the most beautiful stories in all of science. Sadi Carnot was born in 1796, right in the middle of revolutionary France. His father, Lazare Carnot, was a famous military strategist and mathematician, sometimes called the organizer of victory, for his role in the French Revolutionary Wars. So Sadi grew up in a household where rigorous thinking wasn't just encouraged, it was the family business. He trained as a military engineer at the École Polytechnique in Paris, one of the finest technical schools in the world, and he served briefly as an officer. But by his mid-20s, he'd been put on half pay, basically sidelined from active duty, and he found himself with a lot of time to think. And what he thought about was steam engines. Now, here's the context that matters. By the early 1820s, France was watching Britain industrialize at a staggering pace, and a huge part of that industrial dominance was powered by steam. French engineers and politicians were acutely aware that they were falling behind, and they wanted to understand steam engines not just as practical machines, but as a matter of national strategy. Carnot shared that concern, but he approached it from a completely different angle than anyone else. He wasn't trying to build a better engine. He wasn't tinkering with valve timings or boiler pressures. He was asking a question so fundamental that most practical engineers wouldn't have even thought to ask it. Is there a theoretical maximum to how efficient any heat engine can ever be? Not a specific engine, any engine, regardless of how it's built, what fuel it burns, or what working fluid it uses. Think about what a radical question that is. It's like asking, before anyone has built a perfect airplane, whether there's a speed limit for flight that no design can ever exceed. Carnot wanted to find the ceiling. In 1824, he published his only work, a slim book called Reflections on the Motive Power of Fire. It's barely 120 pages, and in it, he laid out an argument so elegant that it still forms the backbone of thermodynamics 2 centuries later. Here's the core of what Carnot figured out, and I want to walk through it slowly because it's genuinely profound. He imagined an idealized engine, what we now call a Carnot engine, that operates in a perfect cycle with no friction, no heat leaking where it shouldn't, no irreversible losses of any kind. A thought experiment, basically. And he showed that even this perfect, impossible engine has a maximum efficiency that depends on only 2 things: the temperature of the heat source and the temperature of the heat sink. That's it. Not the design of the engine, not the material it's made from, not whether it uses steam or air or any other substance. Just the temperature difference. The bigger the gap between the hot side and the cold side, the more work you can extract. The smaller the gap, the less. And no real engine can ever reach even this theoretical maximum. because every real engine has friction, has heat losses, has irreversibilities. Carnot's ideal sets the absolute ceiling, and everything we build lives somewhere below it. Now here's what's quietly amazing about this. Carnot got the answer right even though he was working with a flawed theory of what heat actually is. In 1824, most scientists still subscribed to the caloric theory, the idea that heat was a kind of invisible, weightless fluid that flowed from hot objects to cold ones. Carnot used this framework in his reasoning. He imagined heat falling from a high temperature to a low temperature, like water falling over a water wheel and doing work in the process. The analogy was wrong in its details. Heat isn't a conserved fluid, but the conclusion he reached was correct. It's one of those remarkable cases in science where someone arrives at the right destination by a slightly wrong road. Carnot died in 1832 during a cholera epidemic in Paris. He was 36. His personal papers were mostly burned, as was standard practice to prevent the spread of disease. And his book, that slim volume of reflections, was almost completely forgotten. For about a decade, hardly anyone read it. But then, in the 1840s and 1850s, a handful of brilliant people independently began pulling at the same threads Carnot had tugged, and the whole tapestry of thermodynamics started to unfold. Let's talk about what was happening in the broader scientific world during those years, because it's a fascinating case of an idea whose time had come. Multiple people, working in different countries, often unaware of each other, were converging on the same realization: that heat and mechanical work are different forms of the same thing, energy, and that energy is conserved. It can change form, but it can't be created or destroyed. The person who probably deserves the most credit for establishing this experimentally is James Prescott Joule, a brewer's son from Manchester, England. And I love Joule's story because he's such an unlikely revolutionary. He wasn't a university professor. He wasn't part of the scientific establishment. He was a wealthy young man who ran the family brewery and did physics experiments in his spare time, largely at his own expense. Joule's most famous experiment is beautifully simple in concept. He set up a system where falling weights turned a paddle wheel inside an insulated container of water. The paddle churned the water, and the friction of the churning raised the water's temperature. By carefully measuring the weight that fell, the distance it fell, and the temperature rise of the water, Joule could calculate exactly how much mechanical work corresponded to a given amount of heat. He was measuring the mechanical equivalent of heat, establishing that a specific, precise, repeatable amount of work always produces the same amount of heat, not approximately, exactly. He presented his results to the British Association for the Advancement of Science in 1843 and again in subsequent years, and at first, almost nobody cared. The scientific establishment was skeptical. Here was this brewery owner from Manchester claiming to have measured something fundamental about the universe with paddle wheels and thermometers. But Joule was meticulous, and his measurements kept getting more precise, and eventually the evidence became impossible to ignore. The person who finally gave Joule a serious hearing was a young Scottish-Irish physicist named William Thomson, later Lord Kelvin. Thomson heard Joule present at a meeting in Oxford in 1847, and something clicked. Thomson had been studying Carnot's work, which he'd learned about through a paper by the French engineer Émile Clapeyron, who had rescued Carnot's ideas from obscurity and recast them in mathematical form. Thomson realized that Joule's experiments and Carnot's theory were pieces of the same puzzle, but they seemed to contradict each other. Carnot's framework assumed heat was conserved, that it flowed through an engine like water through a mill, doing work but not being consumed. Joule was showing that heat could be created from work, which meant it wasn't conserved at all. Resolving that contradiction took years of careful thinking, and it was done independently by Thomson in Britain and by Rudolf Clausius in Germany. Between roughly 1850 and 1865, these two men, along with contributions from others, hammered out the first and second laws of thermodynamics. The first law is essentially what Joule demonstrated. Energy is conserved. You can convert heat to work and work to heat, but the total energy in a closed system never changes. It's the universe's bookkeeping rule. Every power plant, every engine, every biological cell obeys it without exception. The second law is subtler and, in some ways, more profound. This is where Carnot's insight gets its full expression. Clausius stated it in terms of a new quantity he invented and named entropy, from the Greek word for transformation. And what the second law says, in its simplest form, is that entropy in a closed system always increases or stays the same. It never decreases. Heat flows spontaneously from hot to cold, never the other way. You can force it to go the other way. That's what a refrigerator does, but only by putting in work from outside. And that work always generates more entropy than you're reducing locally. Here's what that means in practical terms for anyone designing an engine. You can never convert all of the heat from your fuel into useful work. Some of it must always be rejected to a cooler reservoir. Always. That's not a limitation of our engineering skill. It's a law of nature. Carnot's ceiling is real, and it's inescapable. The best you can do is get as close to it as possible by minimizing all the irreversible losses in your system. Friction, turbulence, heat leaking through walls, uncontrolled expansion. And this is where thermodynamics stops being abstract physics and becomes the most practical engineering discipline imaginable. Because once you know the theoretical limit, you can calculate exactly how far your actual engine falls short, and you can start systematically hunting down where the losses are. Every percentage point of efficiency you claw back means less fuel burned, less coal mined, less money spent, less pollution produced. The entire history of engine improvement from the 1850s onward is essentially the story of engineers armed with thermodynamic theory, methodically closing the gap between real performance and the Carnot limit. And the numbers tell that story beautifully. Remember Newcomen's atmospheric engine, the one that first drained the mines? Its thermal efficiency was roughly 1%. 99% of the energy in the coal was wasted. Watt's separate condenser pushed that up to maybe 3 or 4%. By the mid-1800s, the best compound steam engines that expanded the steam through multiple cylinders in sequence to extract more work, were reaching 8, 10, 12%. Still far below Carnot's limit, but each improvement mattered enormously at industrial scale. So thermodynamics gave engineers a map. It told them where the treasure was buried and how much of it existed. But it also pointed toward something provocative. If the efficiency of a heat engine depends on the temperature difference between source and sink, then you want your heat source as hot as possible and your sink as cold as possible. Steam has a natural ceiling. You can only get water so hot before the pressures become unmanageable with the materials available. What if you could use a different working cycle, one that operated at much higher temperatures? That question would lead, eventually, to 2 new types of engine that would reshape the 20th century. And the first of them was conceived by a man working in a patent office in the German city of Augsburg, a man who envisioned an engine so efficient that it would liberate small workshops and individual craftsmen from their dependence on big centralized steam plants. His name was Rudolf Diesel, and his story is one of the strangest and most tragic in all of engineering. A tale of brilliant theory, brutal practical reality, patent wars, nervous breakdowns, and a mysterious death on a foggy night in the English Channel. But before we get to Diesel, we need to talk about the engine that came just before his, the one that first broke free from steam entirely and burned fuel directly inside the cylinder. We need to talk about the internal combustion engine and about a quiet German engineer named Nicholas Otto, who in 1876 built something in a factory in Cologne that would eventually put a motor in every garage, every driveway, every farm in the world. That motor, the four-stroke internal combustion engine, is arguably the single most manufactured complex machine in human history. Billions of them. Literally billions. And it started with Otto. Now, Nicholas Otto wasn't a trained engineer. He was a traveling salesman. He sold tea and sugar and colonial goods across Western Germany in the 1860s. And somewhere along the way, he encountered a description of a gas engine built by a Belgian-born Frenchman named Etienne Lenoir. Lenoir's engine, introduced around 1860, was a real working internal combustion engine. It drew in a mixture of coal gas and air, ignited it with an electric spark, and the expanding gases pushed a piston. It worked. People bought them. But Lenoir's engine was terribly inefficient, maybe 2 or 3%, roughly on par with a Newcomen engine from a century and a half earlier. The reason was simple. Lenoir's engine didn't compress the fuel-air mixture before igniting it. It just sucked gas in and lit it at atmospheric pressure. Think about that for a second. If you light a match in an open room, you get a little puff of heat. But if you could compress all that air into a tiny space first and then ignite it, the explosion would be far more violent, far more energetic, and you'd extract far more useful work from the same amount of fuel. That's the core insight that Otto eventually built his career on. Otto became obsessed with making a better gas engine. He wasn't a theoretician. He didn't sit down with Carnot's equations and derive the optimal cycle. He was a tinkerer, a persistent experimenter, and he had an intuition that compressing the charge before ignition was the key. He partnered with a wealthy engineer named Eugen Langen, and together they founded a company in Cologne, N.A. Otto & C., which later became Gasmotorenfabrik Deutz, a name that still exists today. Their first commercial success was actually an atmospheric engine, a clever but odd design where the explosion flung a free piston upward and then atmospheric pressure pushed it back down on the working stroke. It won a gold medal at the 1867 Paris Exposition, beating out Lenoir's engine on fuel economy. But Otto knew this wasn't the final answer. He kept working. What he was groping toward was the four-stroke cycle. Intake, compression, power, exhaust. Suck in the fuel-air mixture on the first stroke. Compress it on the second. Ignite it at the top and let the explosion drive the piston down on the third. That's your power stroke. Then push the spent gases out on the fourth. 4 strokes of the piston, 2 full revolutions of the crankshaft, 1 power event. It's elegant. It's simple to describe. And it was devilishly hard to make work reliably in the 1870s. Otto built his 4-stroke engine in 1876, and it was a revelation. Compared to Lenoir's engine, it used dramatically less fuel for the same power output. The thermal efficiency jumped to something like 14%, which might not sound impressive to modern ears. But remember, the best compound steam engines of the era were only doing 8 to 12%, and they required a boiler, a furnace, A water supply, a condenser, all of that infrastructure. Otto's engine was self-contained. You fed it gas, you got rotary power. No boiler. No steam. No waiting 20 minutes to get up to pressure. You could put it in a small workshop, a basement, anywhere you had a gas line. And that changed everything for small-scale industry. Here's the thing about Otto, though. He tried to patent the four-stroke cycle itself, not just his specific engine, but the entire concept of compress then ignite. And this led to one of the great patent battles of the 19th century. Because it turned out that a French engineer named Alphonse Baud de Rochas had actually described the four-stroke cycle in a pamphlet published in 1862, 14 years before Otto built his working engine. Baud de Rochas never built it, he just wrote down the theory. But when Otto's competitors dug up that pamphlet, the German courts invalidated Otto's broad patent in 1886. Suddenly, anyone could build four-stroke engines. And they did. The floodgates opened. Two of the engineers who walked out of Otto's own factory in Deutz would go on to become the most famous names in automotive history. Gottlieb Daimler and Wilhelm Maybach left in 1882, partly due to disagreements with Otto about the future direction of engine development. Daimler wanted to build small, high-speed engines that could power vehicles, carriages, bicycles, boats. Otto was focused on stationary industrial engines running on piped coal gas. Daimler and Maybach went to work in a converted greenhouse in Cannstatt, near Stuttgart, and by 1885, they'd built a compact, fast-running gasoline engine and strapped it to a wooden bicycle, creating what many consider the first true motorcycle. A year later, they fitted an engine to a horse carriage. Meanwhile, working independently in Mannheim, just 100 kilometers away, Carl Benz built his own gasoline-powered three-wheeled vehicle, the Benz Patent Motor Wagon, and received a patent for it in January 1886. These two efforts, happening almost simultaneously in southern Germany, are generally regarded as the birth of the automobile, and both of them descended directly from Otto's four-stroke cycle. Now, the shift from coal gas to liquid gasoline was crucial, and it's worth pausing on. Otto's original engines ran on piped gas. You needed a gas supply line, which meant they were tied to cities with gas infrastructure. But gasoline, which was actually a waste product of kerosene refining at the time, petroleum refiners were mostly interested in kerosene for lamps, and the lighter gasoline fraction was so volatile and dangerous that they sometimes just dumped it into rivers. Gasoline turned out to be a spectacularly energy-dense portable fuel. A small tank of it could power an engine for hours. That portability is what made the automobile possible. It's what made the airplane possible. It's what made the entire 20th century transportation revolution possible. And it happened partly because of a fuel nobody initially wanted. But let's come back to Rudolf Diesel, because his story runs parallel to all of this, and it's one of the most compelling in engineering history. Diesel was born in Paris in 1858 to Bavarian parents, grew up poor, was separated from his family during the Franco-Prussian War, and sent to live with relatives in Augsburg. He was brilliant, graduated at the top of his class at the Technische Hochschule in Munich, where he studied under Carl von Linde, one of the pioneers of refrigeration engineering. And it was in Linde's lectures on thermodynamics that Diesel had his great epiphany. He learned about Carnot's ideal cycle, about the theoretical maximum efficiency of heat engines, and he was stunned by the gap between theory and practice. The best steam engines were converting maybe 10 to 15% of the fuel's energy into work. Carnot's limit for the temperature ranges involved suggested you could theoretically get 50, 60% or more. Diesel decided he would build an engine that approached Carnot's ideal as closely as physically possible. His concept was radical. Instead of using a spark to ignite a premixed fuel-air charge like Otto's engine, Diesel proposed compressing pure air to an extreme degree, so extreme that the air temperature would rise to something like 500 or 600 degrees Celsius, hot enough to spontaneously ignite fuel. Then you'd inject the fuel directly into this superheated compressed air, and it would burn smoothly, expanding and pushing the piston down. No spark needed, no premixed explosive charge, just air crushed until it was blisteringly hot, and then fuel sprayed into that inferno. The theoretical advantages were enormous. By compressing to much higher ratios than Otto's engine, Diesel envisioned compression ratios of 20:1 or more compared to Otto's 4 or 5:1. You'd be operating at much higher temperatures, which meant, per Carnot's principle, much higher potential efficiency. Diesel published his theory in 1893 in a paper titled Theory and Construction of a Rational Heat Engine, and it caused a sensation. Here was a young engineer claiming he could build an engine twice as efficient as the best steam engines, running on cheap fuel, small enough for workshops and even vehicles. Investors lined up. The Krupp Steel Works and the Machine and Fabric Augsburg, later MAN, put up money. And then came the brutal collision between beautiful theory and physical reality. Diesel's first prototype, tested in Augsburg in 1893, nearly killed him. The indicator cock, a small valve used to measure cylinder pressure, blew out during a test firing, and metal fragments flew across the workshop. The pressures were far higher than the early materials could comfortably handle. The fuel injection system was a nightmare. Diesel originally envisioned injecting fuel using compressed air from a separate compressor, which worked but added enormous complexity and parasitic energy loss. The seals leaked, the injectors clogged. The combustion was uneven. It took 4 years of grinding, expensive development before Diesel had a working engine he could demonstrate publicly, and even that 1897 engine, while impressive, it achieved about 26% thermal efficiency, roughly double what the best Otto cycle engines could manage, was heavy, finicky, and nothing like the elegant, universal machine Diesel had promised. The stress nearly destroyed him. Diesel suffered severe headaches, depression, and what his contemporaries described as nervous exhaustion. He fought patent battles across Europe. He made and lost fortunes through licensing deals. He became wealthy on paper, but was often cash-strapped in practice. And then, on the night of September 29th, 1913, while crossing the English Channel on the steamer Dresden, bound for a meeting in London, Rudolf Diesel vanished. His bed had not been slept in. His nightshirt was laid out. His watch was left open on the nightstand, as if to mark the time. 10 days later, a body was recovered from the sea by a Belgian pilot boat, and personal items were identified as Diesel's by his son. The body was in such condition that it was returned to the sea, as was the custom. Was it suicide? Almost certainly. His finances, when examined after his death, were in ruins. Debts far exceeding assets. Some conspiracy theories suggested murder, perhaps by coal interests threatened by his engine, or by German naval intelligence trying to prevent him from sharing submarine engine technology with the British. But the evidence, such as it exists, points to a deeply troubled man who saw no way forward. He was 55 years old. And here's the bittersweet part. The engine he created, imperfect, difficult, nothing like his Carnot ideal dream, went on to become one of the most important prime movers in history. Diesel engines today power virtually every cargo ship on the ocean, every freight locomotive in countries that haven't electrified their rail, Lines, most heavy trucks, most buses, construction equipment, generators, agricultural machinery. The modern diesel engine achieves thermal efficiencies of 45 to 50% in large marine applications. Not quite Carnot's ideal, but astonishingly close compared to where things stood when diesel began. He was right about the principle. He just didn't live to see it fulfilled. So by the early 1900s, you've got these two branches of internal combustion. The Otto cycle with its spark ignition, running on gasoline, lighter and faster, destined for automobiles and eventually aircraft, and the diesel cycle with its compression ignition, heavier and more efficient, destined for ships and trucks and industry. Both of them operating at temperatures and pressures that would have terrified the steam engineers of 50 years earlier. Both of them converting chemical energy to mechanical work inside the cylinder itself, eliminating the boiler entirely, making power portable in a way that steam never quite managed. But there was a third type of heat engine waiting in the wings, one that would push temperatures higher still and unlock power densities that neither Otto nor diesel could have imagined. And its origins trace back to a surprisingly simple idea. What if, instead of confining the combustion inside a cylinder and using it to push a piston back and forth, you let the hot gases flow continuously through a spinning wheel of blades? What if you built a turbine that ran on fire? The idea had been floating around since at least the 1790s, when John Barber in England patented a design for what he called a gas turbine, but the materials and manufacturing precision simply didn't exist to make it work. The temperatures involved would melt or warp anything available. It would take more than a century of advances in metallurgy, aerodynamics, and precision machining before anyone could build a practical gas turbine, and when they finally did, it happened in two places almost simultaneously, driven by the most urgent possible motivation: the desperate need for faster military aircraft in the lead-up to and during the Second World War. Because here's the thing about propeller-driven planes. There's a speed limit. As an aircraft gets faster, the tips of its propeller blades start approaching the speed of sound, and when that happens, you get shock waves forming, efficiency drops off a cliff, and you hit a wall. By the late 1930s, the fastest piston-engined fighters were bumping up against that wall, and engineers in several countries realized, almost at the same time, that the way forward wasn't a better piston engine. It was an entirely different kind of engine. In England, a young Royal Air Force officer named Frank Whittle had actually figured this out much earlier than most. Whittle was one of those people who seemed to run on a different clock than everyone around him. Born in 1907 in Coventry, the son of a mechanic, he was small, so small that he was initially rejected from the RAF for not meeting the minimum height requirement. He reapplied, got in on his second try, and quickly distinguished himself as both a gifted pilot and an unusually deep thinker about the future of flight. While still a cadet at the RAF College Cranwell in 1928, at the age of just 21, he wrote a thesis arguing that the future of aviation lay in jet propulsion, in engines that would compress air, mix it with fuel, burn it, and expel the hot exhaust gases at high velocity to generate thrust directly without any propeller at all. Think about what he was proposing. Instead of using combustion to push pistons to turn a crankshaft to spin a propeller to push air backward, you'd just push the air backward directly. You'd suck air in the front, squeeze it, heat it enormously, and blast it out the back. Newton's third law does the rest. For every action, an equal and opposite reaction. The hot gases go backward, the airplane goes forward. Beautifully simple in concept. Whittle patented his design in 1930. And then, almost incredibly, almost nothing happened. The Air Ministry wasn't interested. They evaluated his idea and concluded it was impracticable. The temperatures required would destroy any known materials. The compressor would be too inefficient. The whole thing was a fantasy. Whittle couldn't afford the £5 to renew his patent in 1935, so it lapsed, which meant his ideas became public. He spent years trying to get funding, scraping together support from a handful of private investors, working on his engine in his spare time, while also completing an engineering degree at Cambridge, which he finished with a first-class honors, by the way, because apparently being a visionary jet engine inventor wasn't enough to keep him busy. Meanwhile, in Germany, a young engineer named Hans von Ohain was independently developing the same idea. Von Ohain was a physics student at the University of Göttingen, and he came to jet propulsion from a slightly different angle. He was bothered by the vibration and noise of piston engines and started thinking about smoother, continuous flow alternatives. He patented his own jet engine design in 1936, unaware of Whittle's earlier work. But here's where the stories diverge sharply. Von Ohain had something Whittle didn't. He had the backing of Ernst Heinkel, one of Germany's most ambitious aircraft manufacturers, who immediately saw the potential and threw resources at the project. The result was that von Ohain's engine flew first. On August 27, 1939, just days before Germany invaded Poland and started the Second World War, the Heinkel He-178 took off from Marienhe Airfield near Rostock, powered by von Ohain's Ches-3B turbojet engine. It was the world's first jet-powered flight. The plane wasn't fast by later standards, and the engine only ran for a few minutes. But it worked. The principle was proven. Whittle's engine didn't fly until May 1941, nearly 2 years later, in the Gloucester E-28/39. But Whittle's design turned out to be more practical in the long run, and the British shared his technology with the Americans, who used it to develop the engines for their own early jet fighters. By the end of the war, both sides had operational jet aircraft, the British Gloucester Meteor, the German Messerschmitt Me 262, and the age of the gas turbine had truly begun. Now let's slow down and talk about what's actually happening inside one of these engines, because it's genuinely elegant. A jet engine, a turbojet in its simplest form, has just a few major sections. At the front, you have a compressor, which is a series of spinning blade-covered discs that suck in air and squeeze it to many times atmospheric pressure. Then that compressed air enters the combustion chamber, where fuel is continuously sprayed in and burned, raising the temperature enormously. We're talking about 1,500 degrees Celsius or more in modern engines. Then the hot, high-pressure gases rush through a turbine, which is another set of blade-covered discs, and as the gases push through those turbine blades, they spin the turbine. And here's the clever bit. The turbine is connected by a shaft to the compressor at the front, so the turbine extracts just enough energy from the exhaust gases to keep the compressor spinning, and everything left over blasts out the back as thrust. It's a continuous cycle. Air comes in, gets compressed, gets heated, drives the turbine that runs the compressor, and the remaining energy exits as a high-speed jet of gas. No pistons going back and forth, no intermittent explosions, just a smooth, continuous flow of energy. And because it's continuous, you can push enormous amounts of air through the engine every second, which means enormous amounts of power from a relatively small, light package. The power-to-weight ratio of a gas turbine absolutely dwarfs anything a piston engine can achieve. That's why every commercial airliner you've ever flown on uses some variant of this technology. And I say variant because the pure turbojet where all the thrust comes from the exhaust gases shooting out the back, turned out to be only the beginning. It's great for military fighters that need raw speed, but it's noisy, it's fuel-hungry, and for commercial aviation, engineers found something better. In the 1950s and 1960s, they developed the turbofan, which is what powers almost every large aircraft today. A turbofan takes the basic gas turbine core and adds a large fan at the front, that big spinning disc you can see when you look at the front of an airliner's engine. The turbine in the core drives this fan, and the fan moves a huge volume of air around the outside of the core, bypassing the combustion process entirely. This bypass air provides most of the thrust, and because it hasn't been heated to extreme temperatures, it's much more fuel efficient and much quieter. Modern high-bypass turbofans, like the ones on a Boeing 787, have bypass ratios of 10 to 1 or more, meaning 10 times as much air goes around the core as through it. The result is an engine that converts fuel into forward motion with remarkable efficiency, typically around 35 to 40% thermal efficiency, and when you factor in the propulsive efficiency of all that bypass air, the overall efficiency is genuinely impressive. But gas turbines didn't stay confined to aircraft. And this is where the story connects back to something much closer to your everyday life: electricity. Because it turns out that if you take a gas turbine and instead of using the exhaust to generate thrust, you use the turbine to spin a generator, you've got yourself a very effective power plant. Gas turbine power stations started appearing in the 1940s and 1950s, initially for peak power. Situations where you needed to bring generating capacity online quickly. Because one of the great advantages of a gas turbine is that you can start it up in minutes, unlike a coal or nuclear plant that takes hours. But the real breakthrough came with something called combined cycle power generation. And this is one of those ideas that's so elegant, it almost feels like cheating. Here's how it works. You run a gas turbine, burning natural gas, generating electricity. The exhaust gases coming out of that turbine are still incredibly hot, 500, 600 degrees Celsius. In a simple cycle, you just waste that heat, dump it into the atmosphere. But in a combined cycle plant, you route those hot exhaust gases through a heat recovery steam generator, which is essentially a boiler. The hot gases boil water, make steam, and that steam drives a separate steam turbine, which generates more electricity. You're getting 2 bites at the same energy. The gas turbine extracts work from the high-temperature end, and the steam turbine extracts work from what's left over. Together, modern combined cycle plants achieve thermal efficiencies of 60% or more. 60%. Remember where we started. Newcomen's engine at barely 1%. Watt pushing it to 3 or 4. The best compound steam engines reaching maybe 12. 60% would have seemed like magic to any of those engineers. And that number matters enormously for climate, for economics, for everything. Because when you're burning fossil fuels, efficiency isn't just an engineering bragging point. It directly determines how much carbon dioxide you emit per unit of useful energy. A combined cycle gas plant produces roughly half the CO2 per kilowatt hour of a traditional coal plant, partly because natural gas has less carbon per unit of energy than coal, and partly because of that extraordinary efficiency. So the gas turbine, born from the desperate wartime need for faster fighter planes, ended up transforming how we generate electricity, how we fly, and even how we think about efficiency itself. Whittle and von Ohain, working independently, driven by different motivations, unlocked a technology that reshaped the 20th century. Whittle, for his part, was eventually knighted. But he spent decades feeling bitter about how slowly the British establishment had moved on his ideas. Years of bureaucratic indifference while he was trying to hand them the future. Von Ohain emigrated to the United States after the war and had a long, quiet career in aerospace research. The two men eventually met, became friends, and reportedly held each other in deep, mutual respect. There's something lovely about that. Two rivals who never really were rivals, just two people who saw the same truth at the same time. But while gas turbines and internal combustion engines were transforming transportation and power generation through the 20th century, there was another thread of energy engineering developing in parallel. One that didn't involve combustion at all. One that would eventually become the backbone of modern civilization in a way that none of these heat engines could manage on their own. And its story starts with a series of strange observations about sparks, frogs' legs, and invisible forces, made by curious people who had no idea they were laying the foundation for the entire modern world. Because that's really what happened. These early experimenters, people like Luigi Galvani, who in the 1780s noticed that a dead frog's leg twitched when touched by two different metals, or Alessandro Volta, who around 1800 figured out that the electricity wasn't coming from the frog at all, but from the metals themselves, and built the first true battery by stacking alternating discs of zinc and copper separated by brine-soaked cardboard. These people were poking at something fundamental about the universe without fully understanding what it was. Volta's pile, as it was called, was a revelation. For the first time, you could produce a steady, continuous flow of electric current, not just a momentary spark from rubbing amber on fur, not just lightning captured in a Leyden jar, but a reliable stream of something invisible and powerful. And almost immediately, people started asking, what can we do with this? One of the first answers came from Michael Faraday, and honestly, Faraday might be the most important figure in the entire story of energy engineering, which is saying something, given the cast of characters we've already met. Born in 1791 in South London, the son of a blacksmith, Faraday had almost no formal education. He was apprenticed to a bookbinder at 14, and he did what any curious kid surrounded by books would do. He read them, especially the science ones. He attended public lectures by Humphrey Davy at the Royal Institution, took meticulous notes, bound them beautifully, because of course he could, he was a bookbinder, and sent them to Davy asking for a job. Davy eventually hired him as a laboratory assistant, and the rest is, well, the foundation of electrical civilization. Here's what Faraday figured out, and it's one of those things that sounds simple but changes everything. In 1831, he demonstrated electromagnetic induction. The principle is this: if you move a magnet through a coil of wire, or move a coil of wire near a magnet, you generate an electric current in the wire. No battery needed, no chemical reaction, just motion and magnetism, and out comes electricity. Think about what that means. It means you can convert mechanical energy, spinning, rotating, pushing, pulling, directly into electrical energy. And if you can do that, then suddenly every source of mechanical energy humanity has ever harnessed, water wheels, windmills, steam engines, turbines, becomes a potential source of electricity. Faraday built a simple device to prove it: a copper disc spinning between the poles of a horseshoe magnet, wires attached to the disc's edge and center. Spin the disc and current flows through the wires. It was crude, the voltages were tiny, but the principle was sound, and the principle was everything. Faraday had invented the dynamo, the ancestor of every electrical generator on the planet, every power plant you've ever driven past, every hydroelectric dam, every wind turbine, every nuclear reactor. They all generate electricity using Faraday's principle. They all spin something near a magnet, or spin a magnet near something, and harvest the current that results. The fuel changes, the scale changes, the engineering gets extraordinarily sophisticated. But the core idea is the one that a bookbinder's apprentice demonstrated in a London laboratory in 1831. Now, having a way to generate electricity is wonderful, but it's only half the story. You also need a way to use it, and you need a way to move it from where it's generated to where it's needed. And this is where the story gets really dramatic, because the fight over how to distribute electrical power turned into one of the most famous feuds in engineering history. On one side, Thomas Edison. By the late 1870s, Edison had developed a practical incandescent light bulb. Not the first, he wasn't truly the first, but arguably the first that was commercially viable, lasting hundreds of hours. And he didn't just build a light bulb, he built an entire system: generators, wiring, switches, meters, fuses. Edison thought in systems, which was his real genius. In September 1882, he opened the Pearl Street Station in Lower Manhattan, the first central power plant in America, supplying direct current, DC, electricity to 85 customers within about a 1-mile radius. The lights came on, and the age of electrical power had begun. But here's the thing about direct current. DC flows in one direction, at a constant voltage, and it's very difficult to change that voltage efficiently. This matters enormously because of a simple physical fact. When you transmit electrical power through a wire, some of it gets lost as heat. The amount of power lost depends on the current flowing through the wire. Specifically, it's proportional to the square of the current times the resistance of the wire. So if you double the current, you quadruple the losses. The way to reduce losses is to reduce the current. But power equals voltage times current, so if you want to transmit the same amount of power with less current, you need higher voltage, much higher. And DC systems in Edison's era had no practical way to step voltage up for transmission and back down for safe use in homes. This meant Edison's DC system was fundamentally limited. You couldn't send power more than a mile or two without unacceptable losses. Every neighborhood would need its own power plant. It worked for a dense city block, but it could never scale to light up a whole city, let alone a country. Enter Nikola Tesla and George Westinghouse. Tesla, a Serbian-American inventor of extraordinary brilliance and equally extraordinary eccentricity, had developed a system based on alternating current, AC. In an AC system, the current reverses direction many times per second, typically 50 or 60 times depending on where you are in the world. And here's what's really clever about AC. You can use a beautifully simple device called a transformer to step the voltage up or down with almost no energy loss. A transformer is just 2 coils of wire wrapped around a shared iron core. Feed AC into one coil, and AC comes out the other coil, but at a different voltage determined by the ratio of turns in the 2 coils. More turns on the output side, higher voltage; fewer turns, lower voltage. It's elegant, it's efficient, it has no moving parts, and it completely solves the transmission problem. With AC, you could generate electricity at a power plant, step it up to very high voltage, tens of thousands of volts, eventually hundreds of thousands, send it over long-distance transmission lines with minimal losses because the current is now very small, and then step it back down to safe household voltages at the other end. You could put your power plant wherever it made sense, next to a coal mine, beside a river, out in the countryside, and deliver electricity to cities 50, 100, eventually hundreds of miles away. Edison hated this. He had invested heavily in DC infrastructure, and he fought AC with everything he had, including a deeply unpleasant propaganda campaign. He publicly electrocuted animals, dogs, horses, even an elephant at one point, using AC current, trying to convince the public that alternating current was lethally dangerous. He backed the development of the electric chair, which used AC, specifically so that people would associate Westinghouse's system with death. It was ugly. Edison was a brilliant man, but on this question, he was wrong, and he knew it, and he fought dirty because of it. The decisive moment came in 1893, when Westinghouse won the contract to light the World's Columbian Exposition in Chicago, a massive World's Fair, using AC power. 250,000 lights illuminated the fairgrounds, and millions of visitors saw the future with their own eyes. Then, in 1895, the first major hydroelectric power plant at Niagara Falls began transmitting AC electricity to Buffalo, New York, 26 miles away. The war of currents was effectively over. AC had won, and the basic architecture of our electrical grid, generation, step-up, long-distance transmission, step-down, local distribution, was established. It's essentially the same architecture we use today, more than a century later. And think about what this unlocked. Once you have a reliable electrical grid, energy becomes abstract. It becomes fungible. It doesn't matter whether the electricity was generated by burning coal, by falling water, by nuclear fission, by wind, or by sunlight. Once it's on the grid, it's all just electrons flowing through wires. The consumer doesn't know and doesn't care where their electricity came from. This abstraction is incredibly powerful because it means you can change how you generate electricity without changing anything about how people use it. You can swap out a coal plant for a solar farm, and the lights still come on, the refrigerator still runs, the factory still operates. The grid is the great decoupler, separating energy supply from energy demand in a way that no previous energy system ever could. But building that grid, scaling it up, keeping it reliable, that turned out to be one of the most complex engineering challenges humanity has ever undertaken. Because electricity has a peculiar property that makes it fundamentally different from every other energy carrier we've talked about. You can't really store it. Not easily, not cheaply, not at scale. Coal you can pile up in a yard. Oil you can pump into a tank. Natural gas you can compress into a cavern. But electricity, in the quantities a modern grid requires, has to be generated at almost exactly the moment it's consumed. Supply and demand must be balanced, second by second, across an entire interconnected network, or the whole thing can become unstable. Frequency drifts, voltages sag, and in the worst case, you get cascading failures, blackouts that can spread across entire continents. The Great Northeast Blackout of 2003 is a perfect example. On August 14th, a software bug in an alarm system at a control room in Ohio meant that operators didn't notice when a few transmission lines sagged into overgrown trees and tripped offline. The load those lines had been carrying shifted to other lines, which then overloaded and tripped too, and within about 90 minutes, a cascade of failures spread across 8 U.S. states and the province of Ontario, cutting power to 55 million people. It took days to fully restore. The root cause wasn't a dramatic engineering failure. It was untrimmed trees and a software glitch. But the grid is so tightly coupled, so interdependent, that small failures can propagate in ways that are genuinely difficult to predict. This fragility is something grid engineers think about constantly. They build in redundancy. They maintain spinning reserves, generators that are already running and synchronized to the grid, ready to pick up load instantly if another generator trips offline. They use sophisticated forecasting to predict demand hours and days ahead. And increasingly, they're grappling with a new challenge that brings our whole story full circle, because the fastest growing sources of new electricity generation are wind and solar, and both of them share a characteristic that would have been very familiar to those medieval millers tending their windmills and water wheels centuries ago. They're intermittent. The wind doesn't always blow. The sun doesn't always shine. And unlike a gas turbine, which you can fire up in minutes when demand spikes, you can't make the wind blow harder by turning a dial. This is the great engineering puzzle of our current moment. We have these abundant, clean sources of energy. Sunlight hitting the Earth delivers something like 10,000 times more power than all of human civilization uses. But capturing it, converting it, and especially storing it, and delivering it when and where it's needed, that's where the real engineering challenge lives. And the solutions being developed right now draw on every thread of knowledge we've traced through this whole story: thermodynamics, materials science, electrochemistry, fluid dynamics, control theory. It's all converging. Take lithium-ion batteries, for instance. The basic electrochemistry goes back to Volta's pile, ions moving between electrodes through an electrolyte, converting chemical energy to electrical energy and back again. But the specific chemistry, the materials, the manufacturing precision required to make a battery that can store meaningful amounts of energy, survive thousands of charge-discharge cycles, and not catch fire, that's taken decades of painstaking work. John Goodenough, who co-developed the lithium cobalt oxide cathode that made modern lithium-ion batteries possible, published that work in 1980. He didn't win the Nobel Prize for it until 2019, when he was 97 years old. The gap between the fundamental insight and its full realization is one of the defining patterns in energy engineering. It's almost never one eureka moment. It's a long, slow accumulation of incremental improvements, manufacturing breakthroughs, cost reductions, and sometimes just waiting for the rest of the world to catch up with the idea. Goodenough had the cathode chemistry, but it took Akira Yoshino at Asahi Kasei in Japan to figure out a safe carbon-based anode that could pair with it. And it wasn't until 1991 that Sony commercialized the first lithium-ion battery in a camcorder, 30 years ago. And even then, those early cells were tiny, expensive, and mostly useful for consumer electronics: your Walkman, your laptop, eventually your phone. The idea that you could scale that same basic chemistry up to power a car, let alone buffer an entire electrical grid, would have seemed almost absurd. But here's the thing about engineering: scale changes everything, and sometimes scale is just a matter of will and investment and time. When Tesla, the company, not the man, though Nikola would probably appreciate the naming, when Tesla started seriously pursuing electric vehicles in the mid-2000s, one of their key insights was almost comically simple. Instead of trying to design some exotic new battery format, they just used thousands of small cylindrical lithium-ion cells, the same basic form factor you'd find in a laptop battery pack. They wired thousands of them together with sophisticated thermal management and battery management systems. It was an engineering solution, not a chemistry breakthrough. And over the following decade and a half, as production scaled up and manufacturing processes improved and competition intensified, the cost of lithium-ion batteries dropped by something like 97%. In 1991, a kilowatt-hour of lithium-ion storage cost roughly $10,000. By the early 2020s, that number was hovering around $140, sometimes less. That's not a modest improvement. That's a transformation. And it's the kind of transformation that makes previously impossible things suddenly inevitable. Because here's what cheap batteries mean for the grid. Remember that fundamental problem we talked about? The grid has to balance supply and demand in real time, every second of every day. And if it doesn't, bad things happen? Well, batteries give you a buffer. They let you decouple generation from consumption in time, the same way the grid itself decoupled generation from consumption in space. You generate solar power at noon, when the sun is blazing and demand is moderate. You store it, and you release it at 7 in the evening when everyone comes home and turns on their air conditioning and their ovens and their televisions. That's the basic idea. And grid-scale battery installations are being built right now all over the world. The Hornsdale Power Reserve in South Australia, which went online in 2017, was one of the first big ones. 100 megawatts of Tesla battery packs, built in less than 100 days after Elon Musk made a bet on Twitter that he could do it. It's been expanded since then. And it works. It responds to grid fluctuations in milliseconds, far faster than any gas turbine could spin up. It saved the local grid from multiple potential blackouts. But let's be honest about the limitations, because this is engineering, and engineering is always about trade-offs. Lithium-ion batteries are fantastic for short-duration storage, a few hours, maybe 4 to 6 hours at current economics. That handles the daily solar cycle pretty well. But what about longer gaps? What about a week of cloudy, windless weather in winter? What about seasonal variation, where northern countries get abundant solar in summer but very little in December? For that kind of long-duration storage, lithium-ion batteries are still too expensive per kilowatt-hour of capacity. You'd need enormous quantities, and the cost adds up fast. So engineers are exploring other approaches, and this is where the story gets wonderfully diverse. Some of the ideas are brand new. Some of them are surprisingly old. Pumped hydro storage, for instance, is the oldest and still the largest form of grid energy storage in the world. The concept is beautifully simple. You take 2 reservoirs at different elevations, and when you have excess electricity, you pump water from the lower reservoir up to the higher one. When you need electricity back, you let the water flow downhill through turbines. It's basically a reversible hydroelectric dam. The round-trip efficiency is around 75 to 80%, which is quite good. And the first pumped hydro facilities were built in the 1890s in Switzerland and Italy, over a century ago. The technology is mature, reliable, and long-lasting. The catch is geography. You need the right terrain, 2 reservoirs, and the environmental permitting process can take a decade. But where it works beautifully, and it can store energy for days or weeks, not just hours. Then there's compressed air energy storage, where you use excess electricity to compress air into underground caverns. Old salt mines work well, and release it through turbines when you need power back. There are only 2 large-scale plants in the world right now, one in Germany, built in 1978, and one in Alabama, built in 1991. But new designs are being developed that could improve the efficiency significantly. The old designs waste a lot of energy as heat during compression, but if you capture and store that heat and use it to rewarm the air during expansion, you can push the round-trip efficiency from around 40% up towards 60 or 70. And then there are the truly exotic ideas. Gravity storage, where you lift heavy blocks, concrete, old mine tailings, whatever's cheap and dense, using electric motors when power is abundant, and lower them to generate electricity when it's needed. It's the same principle as pumped hydro, just without the water. There's a company in Switzerland called Energy Vault that's been building systems using massive cranes and concrete blocks. It looks almost surreal, like some kind of industrial ballet. The physics is straightforward. Potential energy equals mass times gravitational acceleration times height, one of the simplest equations in all of physics. But the engineering of making it practical, reliable, and cost-effective at scale is anything but simple. And here's where I want to circle back to something we touched on much earlier in our story, because there's a beautiful symmetry here. We started with fire, the oldest energy technology. Chemical energy stored in wood, released as heat and light. And one of the most promising frontiers in energy storage right now is essentially the same idea, just executed with modern sophistication. Green hydrogen. You take excess renewable electricity, you run it through an electrolyzer, which splits water into hydrogen and oxygen using electrolysis, a process that Faraday himself would recognize. And you store the hydrogen. When you need energy back, you can burn it in a turbine, or better yet, run it through a fuel cell, which recombines hydrogen and oxygen to produce electricity and water. The round-trip efficiency isn't great yet, maybe 30 to 40% through the full cycle, which means you lose a lot of energy in the conversion. But hydrogen has something that batteries don't, honey. You can store enormous quantities of it relatively cheaply in underground caverns or pipelines for weeks or months. It's a seasonal storage solution, and if you're producing it from renewable electricity, the only byproduct is water. The efficiency question is interesting, actually, because it forces you to rethink what efficiency even means in this context. Remember Carnot and his insight that every heat engine has a maximum theoretical efficiency determined by its temperature differential? That framework shaped 2 centuries of engineering. But with renewables, the equation shifts. If your energy source is sunlight and there's 10,000 times more of it hitting the earth than you need, then the cost of the input energy trends toward zero as solar panels get cheaper. In that world, a 30% round-trip efficiency for hydrogen storage might be perfectly acceptable economically, even though it would have horrified a Victorian engineer obsessed with squeezing every last joule out of a ton of coal. The engineering optimization problem changes. It's no longer about maximizing the efficiency of converting fuel to work. It's about minimizing the total system cost of capturing, converting, storing, and delivering energy reliably. That's a different problem, and it requires different thinking. And this brings us to something that I find genuinely moving about the whole arc of energy engineering, if you step back and look at it. Every chapter of this story has been about the same fundamental human impulse, the desire to do more with less, to harness the forces of nature more cleverly, to light the darkness a little longer, to move a little faster, to keep warm, to stay cool, to communicate across distances, to heal, to build. From the first person who figured out how to keep a fire burning through the night, to the Roman engineers who built aqueducts with just enough slope to move water across miles of countryside using nothing but gravity, to the medieval millers who angled their windmill sails to catch the breeze, to Newcomen standing in front of his clanking, steaming, magnificently inefficient engine, watching it pump water out of a mine. Every single one of these moments was someone looking at the world and thinking, I can work with this. I can make this do something useful. And the knowledge accumulated. That's the part that always gets me. Carnot's insight informed Joule's experiments, which informed Thomson and Clausius, which gave engineers the theoretical framework to improve steam engines, which powered the Industrial Revolution, which created the wealth and infrastructure that let people like Edison and Tesla and Westinghouse build the electrical grid, which enabled everything that came after. Faraday spinning a copper disc between magnets in 1831 is directly, causally connected to the wind turbine that might be generating the electricity powering whatever device you're listening to right now. It's one continuous thread. Each generation stood on the shoulders of the one before, and sometimes they didn't even know whose shoulders they were standing on. Think about Goodenough, working on cathode chemistry in 1980, probably not imagining that his work would one day help store the output of solar farms that hadn't been invented yet, feeding into a grid whose fundamental architecture was designed by people who'd been dead for decades, using principles discovered by a bookbinder's apprentice who taught himself science in the basement of the Royal Institution in London in the 1820s. The connections are extraordinary, and they're real. This isn't a metaphor. It's literally how the knowledge and the technology propagated, one mind to the next, one generation to the next, through papers and patents and apprenticeships and arguments and failures and the slow, patient accumulation of understanding. So here we are. The story isn't over, of course. It's never over. Right now, somewhere in the world, an engineer is staring at a computer screen trying to figure out how to make a solid-state battery that won't crack after 1,000 cycles. Somewhere else, a materials scientist is testing a new perovskite solar cell that might be cheaper and more efficient than silicon. In a university lab, someone is running simulations on a fusion reactor design, still chasing that dream of recreating the process that powers the sun, the ultimate energy source, the one that's been raining energy down on this planet for 4.5 billion years, the one that grew the ancient forests, that became the coal that Newcomen pumped water away from, that became the oil that Diesel burned in his engine, that drives the wind and the water cycle and photosynthesis, and essentially every energy source we've ever used except nuclear fission and geothermal. It all comes from the sun in the end, or from the stars that came before it, whose explosions forged the heavy elements, the uranium, the lithium, the cobalt, that we're now learning to use in new ways. The energy was always there. The engineering was learning how to use it. And that's a good thought to rest on, I think. The energy is still there. The wind is still blowing somewhere. The sun will come up tomorrow, and all across the world, people are working, quietly, patiently, brilliantly, on the next chapter of this story. You don't need to worry about it tonight. Tonight, you can just let all of this settle, all these names and dates and machines and ideas, let them drift around in your mind like leaves on slow water, Newcomen's engine clanking away, Watt's separate condenser, Faraday's spinning disk, Tesla's rotating magnetic field, Goodenough's cathode, the hum of the grid outside your window, doing its invisible work, balancing supply and demand, moment by moment, keeping the lights on so you can choose to turn them off, close your eyes, and rest. The story will still be there in the morning. It's been unfolding for a very long time now, and it's not going anywhere. So let it go for tonight. You've followed it far enough. Sleep well.